Much of what we've done regarding the response of dynamical systems has focused on the response of second-order systems. So it isn't very surprising that when we talked in class about things like peak time, rise time, settling times, these time specifications of control systems, that we again turn to second-order systems in order to provide some nice guidelines. We've seen in class and some of the labs, the reason why we do this is oftentimes many systems can be approximated relatively well by second-order systems. One reason for that is because the system has a dominant set of poles. And so if you remember, our poles look like e to the pt, where p is the value of the pole, the location of the pole of our system. And so if we have a set of poles, we could have one pole, one real pole, or we could have a set of complex paired poles that dominate the response. And that is because this p is the closest one to the origin. So again, this is assuming a stable system, and so the one that's closest to the origin are the ones that are going to dominate the response because they're essentially the slowest moving poles. Poles that exist much further out on the real axis, this direction. So if we have a pair of poles out here, that response is going to die away very quickly, and that has to do with this exponent. The larger it is and more negative it is, that means that it's going to die away faster. So what we're interested in understanding is then what are the types of specifications, and what can we say about those specifications if we just have this simple second order system? And that gives us some guidelines for understanding more complex systems. So if we assume that we have a pair of complex poles located at minus sigma and at omega. So the imaginary part is omega and the real part is minus sigma. And here we've explicitly put in the minus sign to indicate that it's stable. And so one way of characterizing, so we're going to describe two ways of characterizing this. One way is simply just by that real and imaginary value of this pole, of these poles. And then the second way we're going to introduce is another nice way when we're talking about time specifications to characterize these poles. So if we write out the denominator, so here this a of s just represents the denominator of our polynomial, and I plug in the two poles, we've done this several times in class and in lab, we multiply this out and we get this quadratic form. And so the constant term, this sigma squared plus omega squared, we're going to call that the undamped natural frequency. And we're going to denote that being omega n squared. And if we look visually at what that implies on the complex plane here, the real and imaginary part, omega n is the magnitude of the vector that expresses that placement of that pole. So it's the length, this gray line represents the length that's given by omega n. And so that's important because that really characterizes the magnitude of the response. And then another useful way, instead of representing the amount of damping in the system, is to, instead of representing it as this real value sigma, we can express it as this funny letter, Greek letter zeta. And that zeta is simply just the sine of the angle theta, which makes this angle from the imaginary axis to the vector angle to our pole. So the reason why we do this is this letter zeta is now not a function of the magnitude. So you can imagine if omega n gets larger, that means that either sigma n or omega is getting larger. And so what defining zeta does is that it defines this angle, which is not really doesn't have anything to do with the length of this vector, or essentially the length of distance from the origin to this pole. So again, we call omega n the undamped natural frequency. So one way you can kind of think about this is you can think about rotating this vector such that it's pointing along exactly the imaginary axis, and we locate that pole on the imaginary axis, essentially without any damping. And then we introduce the amount of damping required to move it from the imaginary axis to this final spot. And so that's the idea of decomposing this in this different way, is that we essentially grab out the magnitude and then we figure out how much we have to rotate that by this zeta in order to place the pole at minus sigma plus or minus omega. So if we make this definitions, then omega n is simply defined by omega squared plus sigma squared. And then we define zeta, the damping ratio, like this. So it's essentially, we've noticed that this when we multiply this out, this is just 2 sigma. And so if we make this definition, where it's essentially the real part divided by that magnitude omega n, then we can express sigma as zeta times omega n. So don't get too confused about just the renaming of all of these variables. The idea again is to decompose the location of these two poles, not just by real and imaginary part, but by essentially magnitude and this damping angle. So we're going to see this used a number of different ways, but one of the first ways is in these time domain specifications. So again, we have, for example, these 4 specifications, rise time, settling time, overshoot, and peak time. And so if we have a simple second order system, so just 2 complex poles and no zeros, that we can characterize in 2 cases exactly, the peak times and the overshoot we can characterize exactly, and the settling time and the rise time we can characterize approximately. We can get this formula, and so by using this formula, then we can understand how changing omega n, or changing the damping ratio, changes the response of this system. So if, for example, we wanted the rise time to be shorter, we would make this omega n larger in order to achieve that. So the reason why we come up with these formulas, the peak time, the reason why those can be exact is that we're effectively finding where the derivative is equal to 0, and we're actually able to solve that solution because we have a solution for the second order system. For the settling time, this settling time is essentially when the response stays within this certain percent envelope. And so what I'm calling percent settle, in this case on the diagram it's 1%, but you could theoretically set it to be something else. And so once this stays within this envelope, that means that the term that goes like e to the sigma t, where this is the real part, so the real part characterizes how much the resulting solution damps out. And so this is really dependent on sigma, and so if I set this approximately equal to 0.01 in this case for 1%, and I solve for this settling time, that I essentially get this formula. And again, remember from the previous slide that this value is essentially equal to sigma based on our definition of zeta. So these provide us some nice formula to understand how the damping ratio and the undamped natural frequency, essentially the location of our poles, but we're just describing them in different ways, not real and imaginary part. Now we're going to describe them by this omega n magnitude and this zeta essentially damping angle. And so we're trying to express where the poles are located and how that impacts all of these time domain specifications. Right now we're not really changing that, but very soon once we get to the feedback control section, we will be doing that.